a planet where the sun never moves. What would your life look like if the star in your sky never rose, never set, and never moved a single degree? Imagine waking up every day under the same frozen sunset, the same direction of light, the same long shadows. On one horizon, a blazing, motionless glare. On the other, a wall of endless night. No dawn, no noon, no true evening. Just a sky locked in place, as if the universe had hit pause. On such a planet, the entire world is divided by light. One hemisphere is a scorching dayside, facing its star forever. Rocks may glow with heat. Any ocean there could be a vast, churning eye of steam. The other hemisphere is a frozen nightside, buried in perpetual darkness, where ice might pile up for millions of years and the constellations never shift. But between these two extremes, there is a narrow ring, a thin twilight zone circling the planet like a scar, where the star hovers forever on the horizon. Here, the sky is locked at a permanent sunset. The light is dim, red, and slanting. Temperatures might hover near the edge of what we call habitable. Winds could roar from day to night, carrying heat and cold in a constant battle. If life can exist here at all, this fragile ring might be the only place it can hold on. This is not just a thought experiment. It should be noted that we know of a real world where this might be true. Wolf 1069b, a rocky planet only about 31 light-years away, orbits a faint red dwarf star in its Goldilocks zone, and is almost certainly locked with one face to its star. In the hunt for alien life, that combination makes it one of the most intriguing Earth-like candidates we have. So what would it actually feel like to stand in that eternal sunset? How would a sky that never changes shape the way we build cities, tell time, or even think about the passage of a day? This means we are not just asking about weather patterns or surface maps. We are asking how flexible life itself can be. Are we rare? A brief accident of mild blue skies and moving shadows? Or can biology adapt to almost anything the universe throws at it, including a world split forever between fire and ice?
So let's begin with Wolf 1069b.
Optimistically speaking, new climate models and early observations are quietly transforming it from a name in a catalog into a place we can almost imagine visiting. So it's time to find out the truth. By the end of this video, we will build a concrete, lived-in picture of a single day in the life on this alien world, under a star that never moves. Why this one quiet red world matters so much. If we want to know what life in our galaxy usually looks like, we cannot just keep staring at stars like the sun. Most stars in the Milky Way are not sun-like at all. They are small, dim, red dwarfs. This means that, statistically, the default setting for life in our galaxy is not an Earth under a yellow star, but a tidally locked, close-in planet circling a cool red ember. In the hunt for alien life, worlds like Wolf 1069b are not the exception. They are the rule. We have already seen this story begin with systems like TRAPPIST-1, 7 Earth-sized planets, all packed tight around a single red dwarf, captured our imagination. But while TRAPPIST-1 is relatively calm for its class, many similar stars are hyperactive, blasting out flares and high-energy radiation that can strip away an atmosphere. It should be noted that if a planet loses its air, its surface water, and any fragile biosphere may follow. Wolf 1069, by contrast, looks quieter and more stable. The star is a cool red dwarf about 31 light-years away, and observations so far suggest low stellar activity. That calmness matters. A steady star gives any atmosphere a fighting chance to survive for billions of years. And around that quiet ember, Wolf 1069b orbits right in the Goldilocks zone, taking about 15.6 days to complete a year. This planet's minimum mass is very close to Earth's, around 1.3 times our own. That puts it firmly in the rocky category, not a gas dwarf. This means that, under the right conditions, liquid water could exist on its surface. Optimistically speaking, Wolf 1069b is one of the most promising nearby Earth-like candidates for a truly habitable environment.
But while TRAPPIST-1's planets pass directly in front of their star from our point of view, Wolf 1069b does not. There is no convenient transit, so we cannot simply let starlight filter through its atmosphere and read off the molecules the way we attempt with TRAPPIST-1e. Instead, we are forced to work sideways, measuring tiny wobbles in the star, feeding those numbers into climate models, and asking what kinds of skies and oceans are even possible. So let's begin to see the stakes clearly. If red dwarf systems dominate the Milky Way, and if calm stars like Wolf 1069 are the best cradles for life, then understanding this single world becomes a test case for our entire picture of the universe. Are our most common neighbors ocean worlds, snowballs, or airless rocks? So it's time to find out the truth by diving into Wolf 1069b's climate, its strange day-night geometry, and the kinds of ecosystems that might cling to its thin ring of eternal twilight, if anything is alive there at all. Meet Wolf 1069b, the hidden Earth next door. So let's begin by actually meeting this supposed hidden Earth next door. If Wolf 1069b is going to rewrite our expectations for life around red dwarfs, we need to understand the quiet little stage it is orbiting. Wolf 1069 itself is not a dramatic sun-like beacon. It is a cool M dwarf, a small red star about 31 light-years away in the constellation Cygnus. In cosmic terms, that is practically the next neighborhood over. This star is only a fraction of the Sun's mass and radius, and it shines with less than 1% of our Sun's luminosity. But while it is smaller and dimmer, that weakness is exactly what shifts its Goldilocks zone inward, hugging close to the star. In the hunt for alien life, that kind of red dwarf system matters enormously. Red dwarfs are the most common stars in the Milky Way, and most potentially habitable planets may orbit them. This means any Earth-like world we find in such a system becomes a template. Is Wolf 1069b that template? On paper, it certainly tries to be. Discovered in 2023 using the radial velocity method, Wolf 1069b tugs gently on its star, revealing its presence through tiny shifts in the star's spectrum. From that data, astronomers estimate a minimum mass of about 1.3 times Earth's. It circles its star once every 15.6 days, in a tight, close-in orbit that still falls squarely within the estimated habitable zone where liquid water could exist on the surface. A year there would pass in just over 2 of our weeks. But what does minimum mass really mean here? Radial velocity only measures how strongly the planet pulls on the star along our line of sight. If the orbit is tilted relative to us, we underestimate that pull. It should be noted that this technique gives a lower bound. The planet could be heavier, but not lighter than 1.3 Earth masses. So we still do not know its exact size or density. Despite that uncertainty, the numbers already tell us something crucial. A planet with roughly Earth-like mass, packed this close to a small star, is extremely unlikely to be a fluffy mini Neptune. At these orbits, low-density gas dwarfs tend to lose their thick hydrogen and helium envelopes over time. Optimistically speaking, Wolf 1069b is almost certainly rocky, a terrestrial world with a solid surface rather than a deep global gas layer. So where is the catch? On the surface, we have a near-Earth mass planet in a Goldilocks orbit around a relatively calm red dwarf. It sounds ideal. Yet everything about whether it is a blue marble or a dead rock hangs on one invisible ingredient we have not measured at all: its atmosphere. Does Wolf 1069b have one? And if so, what kind? So it's time to find out the truth about that missing layer of air and how it could transform this quiet rock into a potentially living world. The tools we have and the ones we wish we had. We have a mystery world and a missing atmosphere. So how do we investigate a planet we can't even see directly? In the hunt for alien life, Wolf 1069b is not a solved case. It is an ongoing investigation, and our first clue arrived only in 2023. Astronomers did not spot this planet crossing its star. Instead, they watched the star itself. Using the radial velocity method, they measured tiny, rhythmic wobbles in Wolf 1069's motion as the planet's gravity tugged it back and forth. From that subtle dance, they pulled out a 15.6-day orbit and a minimum mass close to Earth's.
This means our picture of Wolf 1069b began not with an image, but with a heartbeat in the data. No transits, no silhouettes, just a shifting spectrum telling us, quietly, that something Earth-like was there. But while TRAPPIST-1's planets pass in front of their star and gift us those precious transits, Wolf 1069b does not. When a planet transits, a tiny fraction of starlight filters through its atmosphere, imprinting chemical fingerprints we can study. That is how JWST can probe for CO2, water vapor, or even hints of methane on worlds like TRAPPIST-1e. Wolf 1069b, as far as we know, never lines up that way from Earth's perspective. It should be noted that this robs us of the simplest, most powerful window into its air. So what do we have instead? Right now, our main eyes and ears are high-precision spectrographs on large ground-based telescopes, the same kind of instruments that first revealed the star's wobble. By pushing these tools harder, astronomers hope to refine the planet's mass, search for additional worlds in the system, and maybe glimpse how active the red dwarf really is over time. But they cannot yet peel apart the faint glow of the planet itself. What about the James Webb Space Telescope? JWST is transformative for transiting systems, but for a non-transiting, Earth-sized planet this close to its star, it is almost blind. The glare of the red dwarf overwhelms the planet's thermal signal, and the separation on the sky is far too small for Webb to resolve. So, let's begin to look beyond JWST. The real promise comes from the upcoming generation of extremely large telescopes on the ground. Mirrors 30 to 40 meters across, armed with even sharper spectrographs and advanced starlight suppression techniques. Optimistically speaking, these giants might one day tease out the heat glow of Wolf 1069b, or detect subtle spectral shifts as its dayside and nightside rotate in and out of view. Until then, we are forced into a different kind of astronomy. We take the sparse measurements we do have, mass, orbit, stellar brightness, stellar calmness, and feed them into sophisticated climate simulations. We test thick CO2 blankets, thin Mars-like atmospheres, or something more Earth-like, and watch virtual clouds form and oceans freeze. So it's time to find out the truth in a slower, more patient way. We do not yet have a JWST-style atmospheric verdict. What we have is a verdict in progress. Enough to start asking what daily life there might feel like, and enough uncertainty that any picture we paint could be completely wrong. In the next part, we will step inside those simulations and explore how different atmospheres could transform the same rocky sphere into very different worlds. Two futures for Wolf 1069b: Eden or Iceball. So now we have to face the uncomfortable question head-on. Is Wolf 1069b a hidden oasis or a beautiful dead ice ball? In the hunt for alien life, that is not a poetic choice. It is a brutally literal one. On one side, we have the Eden scenario.
Picture a rocky, Earth-like planet, 1.3 times our mass, wrapped in a thick, protective atmosphere. The red dwarf star, Wolf 1069, hangs in a salmon-colored sky, never moving, because the planet is tidally locked. One hemisphere lives under eternal daylight, the other in endless night. But between them lies a twilight ring, a permanent band of sunrise and sunset, where conditions could be almost comfortable. In this version, the atmosphere does the heavy lifting. It should be noted that even a few bars of carbon dioxide, perhaps mixed with nitrogen and traces of water vapor, can redistribute heat from the dayside into the darkness. Winds howl from hot to cold. Clouds form over the warm substellar region, and rain falls back into long-lived lakes or even a global ocean. This means surface temperatures in the Goldilocks zone of the Terminator could hover around the melting point of water, stable for billions of years. If that is true, complex chemistry has time to play. Ice at the edges, liquid water in the middle, maybe pockets of open ocean near the point directly under the star. A planet-sized laboratory. Optimistically speaking, you can imagine slow, alien ecosystems clinging to that dim, permanent evening, using the steady red light as an energy source, evolving under a sky where the constellations never change. But there is a harsher possibility. What if Wolf 1069b never kept that atmosphere at all? Red dwarfs are quiet today, but their youth is violent. Intense X-ray and ultraviolet radiation, combined with stellar winds, can strip a young planet's air away, molecule by molecule. If that happened here, we end up with the ice ball or bare rock scenario. The dayside becomes a sunburned wasteland, rock heated directly by the star to well above freezing, with no air to spread that warmth. The night side drops toward cryogenic temperatures, approaching the deep cold of interstellar space. No clouds, no weather, just a razor-sharp line between scorched stone and frozen vacuum. Both outcomes are not only possible, they are expected somewhere in our galaxy. Tiny differences in initial water content, magnetic field strength, or early stellar flaring could decide everything. So it's time to find out the truth. Is Wolf 1069b more like a quiet, single-planet version of TRAPPIST-1e, or more like the airless inner TRAPPIST worlds JWST has already ruled out? By the end of this episode, you will have enough data and physical intuition to argue for one side. More than that, you will be able to imagine what it would feel like to actually stand there in the soft twilight of Eden, or on the knife edge between fire and endless night. And in the next section, we will walk onto that surface. Who's talking to you? And where we're going? So, if we are about to walk onto the surface of Wolf 1069b, who is actually taking you there? I'm Host, and this is Channel, where we take single exoplanets and really move in. If you watched our deep dives on the TRAPPIST-1 system, or our breakdowns of other Earth-like worlds in the Goldilocks zone, you know the drill. We do not just list orbital periods and masses. We try to live there, at least in our minds. In the hunt for alien life, it should be noted that this approach matters. Numbers alone do not tell you what a red sky looks like reflected off an ice ocean, or how it feels to stand under a dim red dwarf that never moves. So in this episode, we are going to build Wolf 1069b from the inside out, using every piece of data we have, and clearly marking where the data ends and the thought experiment begins. Here is the roadmap. First, we look at the star itself, Wolf 1069. What kind of red dwarf is it? How quiet is it compared to TRAPPIST-1? And what does that mean for a fragile atmosphere clinging to a close-in planet? This means we will start with stellar activity, flares, and the planet's 15.6-day orbit, because habitability is impossible to judge without understanding the light and radiation that bathe the world. Second, we are going to slow down and really unpack tidal locking and climate physics. What happens to wind, clouds, and oceans on a world where one hemisphere bakes in endless day and the other freezes in eternal night? Is there a narrow ring of dusk, the Terminator, where liquid water and life might survive? Or can a thick atmosphere smear the heat into a more Earth-like climate? Then comes the heart of the episode. We will construct several fully realized versions of Wolf 1069b's surface. One with a dense CO2 greenhouse, one with a more Earth-like atmosphere, and one that is almost airless. In each case, we will ask, what does the sky look like? How strong is the gravity under your feet? What does the wind sound like at the substellar point? Pattern interrupt. What if there is no solid ground at all, but a deep, dark, global ocean lit by a permanent red sun overhead? Only after that will we talk directly about life, possible biosignature gases, energy sources, and how this system compares to TRAPPIST-1e. Optimistically speaking, some of these scenarios are surprisingly habitable, so it's time to find out the truth. Throughout, we will separate hard measurements from speculation, and we will flag every step where we extrapolate beyond current evidence. For the next hour and a half, treat this as a guided relocation. Imagine you have just moved to Wolf 1069b, and together we are going to explore your new home. So, let's begin with the star that makes all of this possible. First principles. What really makes a world habitable? If we have just moved to Wolf 1069b, the first question is simple but brutal. Is this place actually habitable, or are we fooling ourselves? Because before we talk about cities under a red sky or oceans of alien life, we have to be clear what habitable even means. In astronomy, habitable is not a promise of forests, continents, and intelligent beings waving back at us. It is a much narrower, colder idea. Can a planet keep liquid water on its surface in large amounts for billions of years? That is it. No guarantee of biology, just the long-term physical conditions that on Earth allowed life to appear and evolve. In the hunt for alien life, this is our first filter. To understand those conditions, it helps to split the problem in two. First, what does the star provide? Second, what does the planet do with that gift, or that punishment? The star sets the incoming energy, the light, the heat, and the radiation environment. The planet responds with its atmosphere, its rotation, its magnetic field, and its geology. Change either side of that equation, and you can take the same amount of starlight and end up with a frozen desert, a temperate ocean world, or a runaway hell. This is where the famous Goldilocks zone comes in. For any star, there is a band of orbits where an Earth-sized, Earth-like world could, in principle, keep liquid water on its surface. Too close, and water boils away. Too far, and it stays locked as ice. But while this sounds reassuring, it should be noted that the habitable zone is only a starting point. Venus and Mars sit near the edges of our own band. Venus is deep fried by a crushing CO2 atmosphere. Mars is a frozen, thin-aired desert. Same star, similar orbits, completely different outcomes. Around a red dwarf, there is another twist. Because these stars are cool and dim, their habitable zones huddle very close in. This means any Earth-like planet in that band almost certainly becomes tidally locked, showing one face to the star forever. One hemisphere bakes in permanent day, the other lies in endless night. How do you move heat around a world like that? Do you get a narrow ring of twilight, the so-called Terminator, where conditions are mild? Or does the atmosphere collapse and freeze on the dark side? Optimistically speaking, a dense atmosphere and perhaps an ocean can smooth out those extremes, turning a stark, two-faced world into a surprisingly stable, habitable globe. But to know whether Wolf 1069b pulls off that trick, we must start with the central character in this story, the tiny, cool, red dwarf that everything else orbits. So, let's begin by dissecting the personality and history of Wolf 1069 itself, and see what kind of worlds it is capable of making. Inside a red dwarf's glow, who is Wolf 1069? Wolf 1069 is not the kind of star that would grab your attention at first glance. If we could swap our sun for this object, the sky would dim to a deep twilight lit by a small ember-red disk. This is because Wolf 1069 is an M-dwarf, only a fraction of the sun's mass and luminosity, cooler, smaller, and glowing with a rich red-orange hue in visible light. Evaluating a star system for compatibility with life is tricky. A huge part of the story is the planets, but much of it is written by the star they orbit. In the hunt for alien life, M-dwarfs like Wolf 1069 are especially important. They have surface temperatures of just a few thousand degrees, far cooler than the sun, and they radiate most of their energy in the infrared. This means that to receive Earth-like warmth, a planet has to huddle very close in. For Wolf 1069b, that closeness is extreme. Its entire year lasts only about 15.6 days. The planet orbits so near its star that, in our solar system, it would lie well inside Mercury's path. This tight orbit places it in the Goldilocks zone of a very dim star, but it comes with a price: tidal locking. Over time, gravitational tugs slow a planet's rotation until one hemisphere always faces the star. So Wolf 1069b is almost certainly split into eternal day and endless night, with a narrow ring of permanent sunset in between. But while this might sound exotic, it should be noted that stars like Wolf 1069 are not rare curiosities. Red dwarfs are the dominant citizens of our galaxy. Around 3/4 of all stars in the Milky Way are M-dwarfs, including many of the Sun's closest neighbors. This means that, statistically, if life is common in the universe, a huge fraction of it may orbit dim little stars like this rather than sun-like ones. There is a catch. Red dwarfs are often tempestuous. Powerful magnetic fields twist and snap, driving frequent flares that unleash intense X-ray and ultraviolet radiation. Young M-dwarfs can remain violently active for billions of years, bathing close-in planets in particle storms that can strip away atmospheres and water. So let's begin to see the tension. The very stars that offer so many potentially habitable worlds may also be exceptionally good at sterilizing them. Optimistically speaking, Wolf 1069 has one big advantage: time. M-dwarfs burn their fuel with incredible thrift. While a sun-like star survives for about 10 billion years, many red dwarfs can shine steadily for hundreds of billions, even trillions of years. This immense lifespan could give any surviving planet an enormous window for life to emerge, adapt, and perhaps flourish, if it can endure that dangerous stellar childhood. So it's time to find out the truth. Did Wolf 1069b keep its atmospheric shield through that long, violent youth? Or are we looking at a bare, airless rock locked in eternal red daylight? To answer that, we have to descend from the star to the world itself and confront what conditions on its surface might actually be like. A surprisingly quiet neighbor. Why Wolf 1069 gives us hope. If Wolf 1069b's fate depends on its atmosphere, then everything secretly depends on the star itself. So what kind of neighbor is Wolf 1069? A quiet caretaker or a violent wrecker of worlds? Evaluating a star system for compatibility with life is tricky. We focus on the planet, but a huge part of the story is the star bathing it in radiation. Red dwarf stars, in particular, have a reputation. Many of them unleash powerful flares, blasting their close-in planets with X-rays and ultraviolet light. This means thin, Earth-like atmospheres can be stripped away in just a few 100 million years. In the hunt for alien life, that is a serious problem. But while many M-dwarfs behave like this, Wolf 1069 seems different. From the data we have so far, its surface appears relatively calm. Astronomers have monitored its brightness and found only small, infrequent flares, far weaker than the dramatic outbursts we see from stars like Proxima Centauri. Its X-ray and UV output also look subdued compared to the most active red dwarfs. It should be noted that this does not make Wolf 1069 harmless, but it does make it unusual, in a good way. Why does this matter so much for a planet hugging its star every 15.6 days? High-energy radiation is what slowly erodes an atmosphere, molecule by molecule. X-rays and UV photons can ionize the upper layers, allowing stellar winds to physically drag gas away into space. Around a typical flaring red dwarf, a close-in planet might need a crushing, Venus-like blanket just to have any chance of surviving this assault. Wolf 1069's calmer behavior changes that balance. With fewer and weaker flares, the erosion rate should be dramatically lower. Optimistically speaking, this opens the door for a more modest, Earth-like atmosphere to persist over billions of years, even in such a tight orbit. Instead of demanding a super dense shroud of CO2, the star might allow a breathable mix of nitrogen, oxygen, and trace gases to hang on, if it ever formed in the first place. Here is the pattern interrupt. We are used to red dwarfs being the villains of the habitable zone story, but Wolf 1069 might be closer to a quiet, long-lived host, more like a patient landlord than a stellar psychopath. That reframes the narrative from near certain doom to cautious optimism. This system may actually give its planets a fighting chance to keep their air and water. Of course, there is a catch. Our monitoring of Wolf 1069 is still limited in time and precision. Red dwarfs can be sneaky. Some hide long activity cycles or rare, giant flares that only reveal themselves after years of watching. So it's time to find out the truth. Is this star truly as calm as it looks, or are we just seeing a quiet phase? To answer that, we have to move from the star's behavior to the possible climates on Wolf 1069b's surface, and ask what different atmospheres would actually feel like to stand in. How we found a world we can't see. To understand those possible climates, we first have to face a strange fact. We have never actually seen Wolf 1069b. We only know it exists because its star is moving in a very specific, very telling way. In the hunt for alien life, this is one of our most powerful tricks. Back in 2023, astronomers pointed high-precision spectrographs at Wolf 1069, a quiet red dwarf about 31 light-years away. They were not looking for a tiny dot of light from a planet. They were watching the star's spectrum. Over weeks and months, its dark absorption lines slid very slightly toward blue, then back toward red in a repeating pattern. What could make an entire star sway like that? The answer is gravity. A planet and a star do not behave like a small object orbiting a fixed beacon. They both orbit a common center of mass, like two dancers spinning around an invisible point. From our line of sight, that shared motion makes the star wobble toward us and away from us. So let's begin with that wobble. Each time Wolf 1069 moves toward Earth, its light is minutely compressed. When it moves away, the light is stretched. This means the spectral lines shift back and forth in a steady rhythm. This technique is called the radial velocity method, and it should be noted that it does not show us the planet directly. Instead, we read the star like a seismograph. From the timing of the wobble, astronomers measured an orbital period of about 15.6 days. From the strength of the pull, they derived a minimum mass around 1.3 times Earth's. Combine that with the star's mass and brightness, and we get the orbital distance, right inside the Goldilocks zone, where liquid water could exist. But while radial velocity is excellent at weighing a planet and mapping its orbit, it is almost silent about other crucial details. We do not get the exact radius, so we cannot directly compute density. We see no silhouette crossing the star because Wolf 1069b does not appear to transit from our viewpoint. Without that transit, there is no straightforward way to capture starlight filtering through an atmosphere and split it into a detailed spectrum. So what do we do when the usual shortcut to an atmosphere is missing? Optimistically speaking, we squeeze every drop of information from what we do have. Follow-up analysis combined the mass, the tight orbit, and the calm nature of the red dwarf to argue that Wolf 1069b is almost certainly rocky rather than a gas mini-Neptune. Climate models then placed this Earth-like world squarely in the habitable zone, showing that with the right mix of greenhouse gases, dayside oceans could remain liquid even under eternal noon. And yet, there is an irony here. One of the most promising, potentially habitable planets we have ever found is effectively invisible. We infer its nature from tiny shifts in a star's motion, and from computer climates we can never walk through. So how do we explore the weather, oceans, and even possible life on a world we cannot watch transit at all? To answer that, we have to push our models to their limits and imagine what each possible atmosphere would feel like from the surface.
So, could anything actually live there? So if Wolf 1069b is invisible to our telescopes, what can we actually say about whether anything could live there? In the hunt for alien life, this is where we have to stop thinking like tourists and start thinking like climate modelers. Here is what we really know so far. We have a planet with roughly Earth's mass, almost certainly rocky, circling a relatively quiet red dwarf about 31 light-years away. It completes an orbit in just 15.6 days, right in the star's Goldilocks zone, where starlight is, in principle, strong enough to keep water liquid, but not so intense that it instantly boils oceans away. This means, on paper, Wolf 1069b looks like one of the more promising Earth-like worlds in the local universe. But it should be noted that, on paper, is doing a lot of work here. We do not know its true radius. We do not know if it has an atmosphere at all. And there is a deep contradiction hiding in those encouraging numbers. A calm, low-flaring star, a temperate orbit, an Earth-mass planet. It sounds almost ideal. But while that close orbit is great for being in the habitable zone, it almost guarantees tidal locking. One hemisphere is locked in endless day under a tiny orange star that never moves in the sky. The other hemisphere is buried in permanent night, starlight never rising, temperatures plunging toward deep space cold. Can such a world ever be truly habitable? Or does this configuration doom the surface to brutal extremes where only scattered microbes, if anything, could hang on? So it's time to find out the truth, at least in our simulations. To answer this, astronomers turn to 3D climate models, the same kind of tools we use to project Earth's future climate, but now adapted to a tidally locked exoplanet. They feed in the star's spectrum, the planet's orbit, and then vary the invisible ingredients we cannot yet measure: atmosphere thickness, composition, and surface reflectivity. What happens if Wolf 1069b has a dense, CO2-rich blanket like a softer version of Venus? What if it has an Earth-like mix of nitrogen, oxygen, and a little CO2? What if there is almost no atmosphere at all? These simulations do far more than spit out a single average temperature. They map winds that could rush from day to night, clouds piling up under the eternal noon, and dark-side glaciers creeping toward the twilight ring. Optimistically speaking, some scenarios keep liquid water stable around the terminator, forming a thin, habitable ring between fire and ice. And because the models are three-dimensional, we can do something else.
We can step inside them. We can imagine standing on the surface under very different skies. So let's begin. In the next section, we will walk through those virtual climates, one atmosphere at a time, and ask what Wolf 1069b would actually feel like beneath our feet. Reading between the photons. How sure are we, really? But before we step too far into those virtual skies, we need to ask something important. How sure are we that Wolf 1069b is anything like the worlds we're about to imagine? It should be noted that, right now, this planet is invisible to us as a world. We have not seen its surface. We have not split its atmosphere into a spectrum of colors. All we truly have is a subtle wobble in its star's light, radial velocity data that tells us something is pulling on this red dwarf every 15.6 days. This means our planet is, in a strict sense, a pattern in the starlight. From that pattern, we get a minimum mass of roughly 1.3 times Earth's. Minimum is the key word here. Because we do not know the exact tilt of the orbit to our line of sight, the true mass could be higher. Is Wolf 1069b a perfectly Earth-like rock, or a heavier super-Earth with stronger gravity and a thicker atmosphere? The data do not yet say. And it goes deeper. We do not know the radius. We do not know the density. Without a transit across the star, there is no direct way to measure how big this planet is, or whether it is mostly rock, rock plus water, or something stranger. We also have only a snapshot of the star's current calm behavior, not a full biography of its past flares and high-energy outbursts. In the hunt for alien life, that history matters, because a violent youth could strip away a fragile atmosphere long before life ever had a chance. So when we run climate models for Wolf 1069b, we have to make choices. What gases do we put in the atmosphere? How thick is it? Do we start the planet with an ocean's worth of water, a global desert, or frozen ice caps that can slowly melt? Each set of assumptions produces a different, yet physically plausible climate. A steamy, CO2-rich greenhouse. A mild, Earth-like mix with blue seas under a dim orange star. Or a bare, airless rock with a razor-sharp line between blazing day and frozen night. So it's time to find out the truth about this episode itself. We are not claiming to know which version is real. Instead, we will clearly label which parts are pinned down by hard physics, like the orbit and the energy from the star, and which parts are speculative extrapolations built on those foundations. Here is the pattern interrupt, that speculation is not a weakness. Optimistically speaking, it is the whole point of frontier science. By exploring multiple versions of Wolf 1069b, we learn what to look for next. Which atmospheres could JWST or future giant telescopes actually detect? Which climates would leave fingerprints in the starlight? In other words, imagining these worlds is how we design the observations that will finally tell them apart. So let's begin to use our uncertainty as a map, not a mistake, as we step into the next set of possible skies over Wolf 1069b. From orbit to oceans, big picture habitability on Wolf 1069b. So let's begin by pulling all the pieces together and asking a simple question. If we could float above Wolf 1069b and see the entire system at once, would it look friendly to life or hostile? In the hunt for alien life, this is where we zoom out before we dive in. Wolf 1069b is, as far as we know, the only planet hugging this quiet red dwarf in its Goldilocks zone. It races around its star once every 15.6 days, so a year there is just over 2 weeks. But while the orbit is tight, the energy is not extreme. Because the star is so dim, the planet receives roughly Earth-like total starlight, just packed into a much more compact system. To see how compact, compare it to our own backyard. Mercury orbits the Sun at about 58 million kilometers. Wolf 1069b is far closer to its star than that, yet it is not automatically a scorched world. This means the faint red glow of the host star compensates for the close orbit, creating a zone where liquid water could exist on the surface if the atmosphere cooperates. It should be noted that such a close orbit almost certainly means tidal locking. One hemisphere faces the star in eternal day, the other is trapped in endless night. At first glance, that sounds disastrous for habitability. Would the day side roast while the night side freezes into an airless glacier? Climate models suggest the situation is more nuanced. With many plausible atmospheres, especially ones containing CO2 and perhaps some water vapor, winds and circulation can efficiently redistribute heat, softening the contrast between blazing noon and frozen midnight. In these simulations, the day side does not have to become a Venus-like furnace, and the night side does not have to collapse into a deep freeze that steals the entire atmosphere. Instead, broad regions, especially around the terminator ring between day and night, can remain temperate enough for liquid water. Optimistically speaking, whole belts of the planet could be habitable at once. There is another quiet advantage. Unlike the TRAPPIST-1 system, where 7 planets tug and resonate with one another, Wolf 1069b has no confirmed neighbors, no crowded chain of worlds, no complex gravitational dance. This relative isolation may make its long-term orbit more stable and its climate evolution simpler, without constant orbital stretching to drive extreme volcanism or drastic ice ages. So it's time to find out the truth about what kind of world that stable stage is hosting. In the next sections, we will walk through several different versions of Wolf 1069b. A thick CO2 greenhouse with steamy oceans, an Earth-like atmosphere with blue skies and scattered clouds, and an almost airless rock where water, if it exists at all, hides in shadows. Each scenario feels like a different planet entirely. Which one matches reality, and which one would be best for life, might surprise us. Locked in place. How tidal locking rewrites the rules of weather. So if each atmosphere could turn Wolf 1069b into a different world, there's one feature that all of those versions almost certainly share. The planet is probably locked in place. In the hunt for alien life, we often picture an Earth-like world spinning under a rising and setting sun. But while that's our experience, it is not the default outcome for planets huddled close to a red dwarf star. Strong tidal forces act like a cosmic brake, draining rotational energy until one hemisphere always faces the star. This means Wolf 1069b is very likely tidally locked, just as our moon always shows us the same face. So let's begin with the geometry of such a world. Above one point on Wolf 1069b's surface, the dim red star would hang motionless, forever pinned at the zenith. This is the substellar point, a bullseye of unending daylight. Move outward from that point, and the star sinks lower and lower toward the horizon, until you reach a narrow ring encircling the planet where it never quite rises and never quite sets. Beyond that twilight band, you cross into a hemisphere that never sees the star at all, an eternal night lit only by starlight from the wider universe. It should be noted that this strange lighting pattern completely rewrites the rules of weather. At the substellar point, intense heating drives air to rise continuously, like a permanent global thunderstorm. That hot air then flows outward at high altitude toward the night side, cools, and eventually sinks into the darkness before racing back along the surface toward the light. The entire atmosphere becomes a giant heat engine, pumping energy from day to night in a circulation pattern that has no real analog on Earth. If Wolf 1069b has oceans, they would join this redistribution game. Warm water under the perpetual red glare could flow toward the terminator, releasing heat into the twilight and preventing it from freezing solid. In climate simulations of tidally locked planets in the Goldilocks zone, that dusk ring often emerges as the most stable, habitable region. Not too hot, not too cold, with temperatures hovering around the range where liquid water, clouds, and maybe even complex chemistry can persist for billions of years. Optimistically speaking, that thin band could be where life digs in.
But what would it actually feel like to live there? If your entire civilization grew up in that eternal sunset, would you have any real sense of time of day? The star would just sit there, glowing red on the horizon. You might track subtle brightening and dimming as clouds drift past, or as your orbit carries you slightly closer or farther from the star. But a dramatic sunrise or sunset, as we know it, would never occur. And what about the night sky? Walk just a little way into the permanent dark, and the stars would blaze with extraordinary clarity. Yet the red dwarf itself would never rise. Would day mean facing the hidden star, and night mean facing the galaxy instead? So it's time to find out the truth about which of these regions, blazing dayside, frozen nightside, or that twilight ring, actually gives Wolf 1069b its best shot at being truly habitable. Scenario 1. The thick CO2 greenhouse world. So if you stood where that hidden star hangs directly overhead, what kind of world would actually surround you? In the hunt for alien life, one of the most powerful tools we have is not a telescope, but climate models. They let us ask a simple question. What if Wolf 1069b wrapped itself in a deep, heavy shroud of air? So let's begin with scenario 1, a thick CO2 greenhouse world. Imagine an atmosphere not like Earth's gentle 1 bar, but several bars of pressure dominated by carbon dioxide. This means the air behaves like a vast thermal blanket, trapping the faint energy from the red dwarf and refusing to let it escape back into space. Under a star as cool and dim as Wolf 1069, that extra trapping is not just a detail, it is the difference between a frozen snowball and a truly habitable planet. Because the planet is almost certainly tidally locked, you might expect the night side to plunge toward absolute zero. But while airless rocks do exactly that, a thick CO2 atmosphere changes everything. High pressure and dense gas allow heat to flow efficiently from the blazing day side to the dark hemisphere. Powerful winds and global circulation cells smear out temperature extremes, so the night side glows with a deep infrared warmth instead of freezing solid, and the substellar point avoids turning into a sterile furnace. Now picture yourself at that substellar point. The red dwarf star is fixed high in the sky, a deep ember-red disk shining through a hazy, copper-tinted atmosphere. The light is dimmer than noon on Earth, yet the heat feels heavy, pressing in with the weight of several bars of pressure. Above you, thick cloud decks swirl, their undersides glowing faintly as they trap infrared radiation. At the surface, there might be a global ocean, its dark waters absorbing the crimson light, while relentless winds roar overhead, racing away toward the eternal night. Climate simulations for such a system suggest that, with a few bars of CO2, large swaths of the day side could stabilize comfortably above the freezing point of water. It should be noted that the hottest regions, near the exact substellar point, might climb well above Earth-like tropics, but the surrounding day side, and especially the terminator, could linger between 0 and perhaps 30 degrees Celsius. In those broad belts, liquid water could pool in seas, lakes, and rain-soaked lowlands. What would that mean for life? Optimistically speaking, this world would be hot, humid, and stormy, but also astonishingly dynamic. Thick clouds would drive an intense hydrological cycle, constant evaporation under the fixed star, towering thunderheads near the substellar point, and endless rain sweeping into the twilight ring. In sheltered bays and along cooler coasts at the terminator, complex weather patterns could carve out long-lived niches. Could dense microbial mats cling to rocky shores, or even macroscopic organisms cruise the warm, dim oceans, forever under a red sun that never sets? So it's time to find out the truth. Is this steamy greenhouse the best Wolf 1069b can offer? Or is there an even more Earth-like possibility waiting in our next scenario? Scenario 2, an almost Earth sky under a red sun. So what if Wolf 1069b is not a steamy greenhouse at all, but something far more familiar? What if, against the odds, we step outside our lander and the air feels almost like home? In this second scenario, we give the planet roughly 1 bar of atmosphere, similar to Earth. Nitrogen does most of the heavy lifting, with a dose of CO2 to keep things warm, and, if life has had time to work its slow magic, a trace of oxygen as a biological fingerprint. In the hunt for alien life, this is the dream case, a stable, Earth-like blanket of air wrapped around a rocky world in the Goldilocks zone of a quiet red dwarf star. But while the pressure might feel familiar, the climate would not. An Earth-thickness atmosphere can still move heat from the bright side to the dark. Yet on a tidally locked planet, the job is harder. This means the substellar point under the red sun could be comfortably warm, the twilight ring mild, and the far night side bitterly cold. Instead of smooth day-night cycles, you get sharp transitions, blazing zenith, eternal sunset, and frozen midnight, all existing at once. Where would we live? Most likely in the twilight ring, the band of permanent evening encircling the planet. Step outside there, and the star never climbs or sets. It just hangs near the horizon, a deep orange ember. The sky would glow in permanent golden red, like the last minutes of an Earth sunset stretched across your entire life. Shadows would be long and motionless, pointing forever toward the substellar point. Time, at least visually, would stand still. It should be noted that the weather would not. Imagine jet streams wrapped like fixed hoops around the terminator, with storm tracks that hardly drift at all. Storm systems could march endlessly along the same atmospheric highways, tracing the line between day and night. Coastal regions in that eternal dusk might have predictable rainy belts, while inland plateaus bask in stable, cool conditions. Shallow seas could hug the sunset zone, their surfaces rippling under steady, directionally consistent winds. How would humans adapt to a sky that never changes? Do we still talk about morning and evening when there is no sunrise? Our circadian rhythms would need to decouple from light and latch onto something else. Perhaps we organize our days by subtle temperature cycles, as the atmosphere slowly breathes heat from dayside to nightside. Or we time our activities by the regular arrival of those terminator storms. Architecture would also transform. Cities might be built with every window facing the fixed star direction, like sunflower fields frozen in place. Streets could be aligned along the permanent shadow lines, using the unchanging light for navigation. Optimistically speaking, an entire culture could grow up reading the sky, not by motion, but by color and wind. So let's begin to ask a deeper question. If such an almost Earth exists around Wolf 1069, how would we ever know from across 31 light years? Scenario 3.
the bare rock and the frozen dark. So let's begin to ask an even harsher question. What if Wolf 1069b never became that almost Earth at all? What if, instead, it's a warning label for planets around red dwarfs? In the hunt for alien life, we often imagine atmospheres as a given. But while Earth's air feels automatic to us, it is actually fragile. Around a young red dwarf, that fragility is exposed. Wolf 1069, like other M dwarfs, would have spent its youth flaring and blasting its inner system with high-energy radiation and charged particles. This means any early atmosphere on Wolf 1069b could have been stripped away, molecule by molecule, before complex chemistry ever had a chance to settle in. In this pessimistic scenario, the planet is left with only a whisper of gas, a tenuous exosphere, perhaps a few residual atoms of oxygen or sodium lofted from rock, but no real air, no clouds, no weather. The sky would be pure black, even at noon, the red star a hard, unblinking disk hanging over a dead horizon. It should be noted that without pressure, liquid water cannot exist on the surface for long. It either boils away or freezes into vacuum-baked ice. What does that do to temperature? Near the substellar point, where the star stands fixed overhead, bare rock absorbs brutal radiation with nothing to scatter or soften it. Local temperatures could soar far above the melting point of lead, while unfiltered ultraviolet and X-rays rake the ground. Step a few hundred kilometers away, however, and the heat drops off a cliff because there is no atmosphere to carry it sideways. On the night side, the opposite extreme rules. Eternal darkness, no starlight, and almost no internal heat escaping from the planet's interior. Rock and ice radiate their energy straight into space. Over millions of years, much of that hemisphere could sink toward cryogenic temperatures, only a few tens of degrees above absolute zero. Any volatile gas that did escape earlier might end up frozen here as a thin, glassy frost. Between these two hells lies the Terminator, a razor-thin ring where day meets night. In a world with air, this could be a Goldilocks zone, a band of twilight seas and windswept clouds. Here, with almost no atmosphere, it is just a line on the ground. Temperatures might briefly cross through habitable values, but only in a skin of rock a few centimeters deep. So is life impossible here? Not necessarily. Even on such a bare rock, the subsurface tells a different story. A thicker crust can insulate heat from radioactive decay and tidal flexing. A kilometer or 10 below the surface, pressure rises, temperatures stabilize, and ancient ice deposits could melt into buried aquifers. Around localized geothermal hotspots, cracks in the rock might host thin films of liquid water, clinging to mineral grains in total darkness. On the deep night side, layers of ice, tens or hundreds of meters thick, could trap pockets of brine, warmed from below and sealed from space. Microbes there would never see Wolf 1069 at all. Their sky would be rock. Their sun would be chemistry, gradients of dissolved minerals, perhaps hydrogen and methane, produced by water-rock reactions, just as we see near hydrothermal vents on Earth. To us, this planet would feel almost incomprehensibly alien. No air to breathe, no blue sky, no clouds, no sound. Step outside a habitat, and there is only harsh vacuum and the red star glaring silently over a scorched plain. Any life that did evolve would live and die underground, blind to the wider universe, never knowing that just above the rock ceiling, a star burns. So it's time to find out the truth. From 31 light years away, could we ever detect such hidden, buried biospheres? Or would Wolf 1069b look in every telescope we build like nothing more than a silent, frozen stone? Weather on a world without sunrise. From a distance, that silent, frozen stone is all we see. But if Wolf 1069b does have an atmosphere, what would the weather be like on a world where the star never rises
and never sets. So let's begin with the most striking feature of a tidally locked, potentially habitable planet, the substellar point. This is the spot directly under the red dwarf, where the star hangs motionless at the zenith. Constant stellar heating there drives relentless updrafts. Warm air rises, cools, and condenses, building what many climate models predict for such worlds, a towering, permanent storm, or at least a dense, bright cloud deck fixed under the star. Can you imagine a sun that never moves, always hidden behind a vast, boiling shield of cloud? This means the entire global circulation is organized around that one bright bullseye. Air heated at the substellar point ascends, then spreads outwards high in the atmosphere, racing toward the night side. Strong east-west jets would likely wrap the planet, acting like conveyor belts that transport heat and moisture into the darkness. Over the perpetual night hemisphere, the air cools, grows dense, and sinks. Down there, under a sky of endless stars, the descending air would be dry and stable. It should be noted that this could create enormous regions of crystal-clear, pitch-black nightside, where the Milky Way might blaze brighter than anything we have ever seen on Earth. But while Earth's cloud patterns march across the globe with the day-night cycle, Wolf 1069b's clouds would be almost nailed in place. They would track geography and geometry, not time. Mountain ranges near the terminator could anchor standing cloud walls. The substellar storm would barely drift. Optimistically speaking, that stability might produce long-lived climate zones, a bright, humid eye under the star, a cloudy, temperate ring around it, and a cold, clear desert of night beyond. Yet within each zone, the weather could be intense, with deep convection and powerful winds that never take a break. The hydrological cycle would look alien as well. On Earth, storm systems travel. Rain chases fronts and seasons. Here, imagine instead a ring-shaped band of frequent rain wrapped around the twilight belt. Moist air, rising from the bright side, flows outward, cools near the terminator, and drops its water in almost the same places over and over again. Near the exact substellar point, air might be too strongly upwelling and too dry aloft for constant heavy rain, while the deep night side, with its sinking, desiccated air, could be nearly rainless. So what would it feel like to live there? Picture a city built right on the terminator line, where the star forever hangs low on the horizon. The forecast would sound strangely repetitive. Chance of showers in the late afternoon? There is no afternoon. Instead, meteorologists might say, persistent light rain, broken clouds, steady winds from the dayside, indefinitely. In the hunt for alien life, such pinned-in-place climate patterns could be a gift. Biospheres love stability. But could life adapt to a sky that never changes, under winds that never sleep? Or would it still be driven into the dark and the deep? So it's time to find out the truth about how we might actually test that from 31 light-years away. Skies, colors, and seasons under a red dwarf. So if the winds never sleep and the day never ends, what does a sky even mean on Wolf 1069b? On a world locked to a single, dim, red dwarf, the heavens are not a clock that turns. They are a backdrop that barely moves at all. So let's begin with the light itself. Wolf 1069 is a cool red dwarf, radiating most of its energy in deep reds and near infrared, rather than the balanced rainbow we get from the sun. This means the planet's surface would be bathed in a coppery, rust-tinted glow. Greens would look darker, almost black in the shade. Blues would be muted and grayish. Any reflective ice near the night side would not sparkle white, but blush faintly red like snow at permanent sunset. At the substellar point, though, it would still be bright. Wolf 1069b orbits close in, deep in that tight Goldilocks zone, so even a faint star can rival our noon. Models suggest the total energy hitting the top of its atmosphere could be within a factor of 2 of Earth's. So standing directly under the star, you might squint, as you do on a hazy afternoon here.
bright enough to cast sharp shadows, but with a darker, blood-red sky, rather than Earth's cobalt blue. Move away from that center, and the sky becomes stranger. On a perfectly tidally locked, low obliquity world, the star never rises or sets. Instead, its disk simply sinks toward the horizon and freezes there. Around the terminator, you would live under a permanent band of twilight, a gradient from deep red near the star through burnt orange to a dim purplish gray overhead. It should be noted that this line is not just a border of light and dark, it is a border of color. Molecules in the atmosphere would scatter the red dwarf's light differently from Earth, shifting familiar hues in eerie ways. Then, one step farther, and the star is gone. On the night side, the sky would be almost perfectly black, except for the thin halo of the lit hemisphere over the horizon, and the sharp, icy stars of the wider Milky Way. In the hunt for alien life, this is where charged particles and magnetic fields might paint slow, ghostly auroras, rippling permanently over a frozen ocean or a solid, glacial cap. But without seasons, how would anyone here tell time? On Wolf 1069b, traditional seasons barely exist. The climate is defined by where you stand, not when you live. This means any life and any civilization would probably build its entire idea of time from the subtle. Small shifts in wind, tiny changes in atmospheric circulation, or the rare flare from its quiet red dwarf. Optimistically speaking, their cosmology would be born from a sky that almost never changes, forcing them, and us, to look much more closely at every faint variation.
So it's time to find out the truth about whether those variations are something our telescopes could ever see. Could life adapt to a world split in half? So if the sky barely changes, could life itself change enough to survive a world split in half? On Wolf 1069b, every ecosystem would be forced to answer that question with its own biology. In the hunt for alien life, we usually imagine green forests under a yellow sun. But here, the star is a cool red dwarf, glowing mostly in red and near infrared. This means that if photosynthesis evolved, it would not waste a single photon. Pigments might be tuned to those longer wavelengths, absorbing almost everything that hits them. Instead of bright green, vegetation could be deep purple, dark brown, or even nearly black, carpeting the substellar region where light is constant and strong. From orbit, an alien satellite might see a dark eye staring back from the day side of the planet. However, the very center of that eye might be too intense. Near the exact substellar point, temperatures and radiation could be brutal. So it should be noted that the true sweet spot for complex life may be the twilight ring, the narrow band of eternal sunset around the terminator. Here, light is softer, temperatures are moderate, and conditions might stay in the Goldilocks zone for billions of years. Imagine an entire biosphere compressed into a glowing halo encircling the planet. Forests and oceans wrapped in a band only a few hundred kilometers wide. Crowded, competitive, but astonishingly stable. What about the night side? Frozen under unending stars. If an atmosphere and oceans can move heat around, some regions there might hover just above the freezing point. But even in deeper cold, life could tap other energy sources. Chemosynthetic microbes might cluster around geothermal vents, just as they do in Earth's deep oceans, feeding on chemical gradients instead of starlight. Subsurface aquifers could circulate water from the warm day side toward the cold night, creating a planetary-scale battery of dissolved minerals and oxidants. Bacteria-like organisms might live entirely in rock pores, never once seeing the sky. Over time, these ecosystems would breathe into the atmosphere. Photosynthetic organisms on the day and twilight sides could release oxygen. Methane might leak from anaerobic microbes in bogs or subsurface habitats. Nitrous oxide could be a byproduct of alien nitrogen cycles.
So let's begin to imagine an atmosphere where oxygen and methane coexist in amounts that should not be stable without constant replenishment. From light years away, that chemical imbalance would be a shout into the quiet of the universe. But if intelligent life arose in that eternal sunset band, how would they see their own planet? Would they dare expeditions into the blazing day or the silent dark? Or would those regions become realms of myth and fear? Optimistically speaking, their first true science might begin the moment someone steps beyond the glow of their twilight home, and what they find there could change everything. So it's time to find out the truth about what our telescopes might see if such a world is truly alive. A day in the life on Wolf 1069b. So what does an actual day look like on such a world if there is no real day at all? In the hunt for alien life, it's not enough to talk about orbits and atmospheres. We want to know, what would it feel like to stand there, to live there, to build a home under a red dwarf sky? So let's begin in the twilight. Our imagined settler wakes inside a low, curved habitat on the terminator of Wolf 1069b in the narrow band where liquid water can exist. Outside, the star is frozen just above the horizon, a deep orange disk that never rises and never sets. This means the light slants in from the same direction every hour of every year, painting permanent shadows across the settlement's clustered domes. There is no alarm clock tied to sunrise. Instead, time is measured by the subtle breathing of the planet. As the morning shift starts, winds pick up slightly, flowing from the cold night side toward the warm substellar region. Temperatures climb by a barely noticeable degree. Thin clouds drift across the fixed star, dimming and brightening the landscape in slow, gentle pulses. It should be noted that here, people feel the passage of time in the air on their skin, not in the motion of the sky. The habitat itself is oriented like a sundial, frozen mid-gesture. Windows and solar collectors face the star directly, armored against its constant glare and flares. Thick walls insulate against a climate that is stable on average, yet sharply different if you walk just a few dozen kilometers toward day or night. Inside, clocks and displays simulate a 24-hour rhythm borrowed from Earth-like worlds, because biology still needs a cycle, even when the planet does not provide one. Work for the day? A survey trip toward the brighter side. Vehicles hug the ground, streamlined for the persistent crosswinds that sweep along the terminator. As the team travels toward the substellar point, the air grows warmer, the sky brighter, the clouds higher. Optimistically speaking, shallow seas here might steam gently, fed by a thick, protective atmosphere that spreads heat around the globe. But while the energy is abundant, so is danger. Step too far, and the world becomes a desert of blinding light and punishing heat. On other days, expeditions move into the night side, chasing science rather than sunlight. Each kilometer brings deeper cold and thinner clouds, until the landscape fades under a sky rich with stars. Navigation is easy in one sense. The star is always back there, glowing at the horizon like a permanent lighthouse. Permanent constellations and the red dwarf's fixed position become the compass roses of this system. Clothing is designed for constancy, not seasons. Layered, wind-resistant fabrics, face shields tuned to the red glare. Thermal systems that can add or shed only a modest amount of heat. Life here has adapted to gradients rather than cycles. Whether engineered humans or native organisms, bodies might specialize along the band. Robust, heat-tolerant forms closer to day. Slow, insulated forms edging into night. As the shift ends, our settler walks alone toward the boundary of darkness. Behind, the settlement glows in a permanent sunset. Ahead, the terrain drops into black, illuminated only by stars so dense they seem to merge into a silver river. The red dwarf peaks just above the horizon, a dim ember compared to the Milky Way blazing overhead. Standing there, balanced between eternal day and eternal night, they realize that this strange routine is still written by familiar physics. Heat flows from hot to cold, Atmospheres circulate. Planets orbit their stars in quiet obedience to gravity. And on a world where the sun never moves, the search for a rhythm of work, of rest, of life itself becomes the deepest connection back to Earth and to every other habitable world we might one day find. How Wolf 1069b stacks up against TRAPPIST-1 and friends. On a world where the sun never moves, what kind of planetary neighborhood gives that frozen sky its context? If Wolf 1069b is one quiet apartment in the galaxy's housing market, then TRAPPIST-1 is a crowded, glowing high-rise right next door. So let's begin with that high-rise. The TRAPPIST-1 system sits about 40 light-years away, built around an ultra-cool red dwarf only slightly larger than Jupiter. 7 rocky, Earth-sized planets huddle close in, several inside the narrow Goldilocks zone where liquid water could exist. Because they pass directly in front of their star, from our point of view, each transit lets us peel back a little more of their atmospheres, temperatures, and orbits. In the hunt for alien life, this is a dream setup for collecting data. Wolf 1069b, by contrast, is alone. As far as we know, there is just one detected planet, and it does not transit its star. This means we found it by the tiny gravitational tug it exerts, not by watching it cross the stellar disk. The result? TRAPPIST-1 gives us a detailed family portrait, while Wolf 1069b is more like a silhouette. We know its minimum mass, its 15.6-day orbit, and that it sits in the habitable zone, but the fine print of its atmosphere remains hidden. But while TRAPPIST-1 is rich in information, it is also rich in danger. Its red dwarf star, though relatively calm for its class, still throws out strong flares and high-energy radiation. JWST has already shown that the inner planets are probably stripped of thick atmospheres. It should be noted that even TRAPPIST-1e, the prime Earth-like candidate, is under intense scrutiny, because that radiation may have eroded more air than we hoped. Wolf 1069, on the other hand, appears remarkably quiet. Fewer flares, less harsh ultraviolet, a calmer stellar wind. This means that over billions of years, a planet in the Goldilocks zone has a better chance of holding on to its atmosphere, if it ever had one. Optimistically speaking, this could make Wolf 1069b a more stable surface for liquid water than many of the TRAPPIST-1 worlds. Here is the pattern interrupt. TRAPPIST-1 feels like the obvious favorite, right? 7 planets, perfect transits, JWST staring straight at them. Yet from a purely environmental standpoint, Wolf 1069b might be the safer cradle for life. Both systems push their planets close, forcing tidal locking and permanent day-night divides. But while TRAPPIST-1's planets endure a harsher radiation bath, Wolf 1069b orbits in a dimmer, gentler glow. So it's time to find out the truth. Does our best long-term hope lie in the system we can see most clearly, or in the quiet world that refuses to cross its star? To answer that, we need to imagine what Wolf 1069b's hidden atmosphere could actually be like, and how different versions of that invisible shell would rewrite the story of its habitability. Can our telescopes ever see its air? If Wolf 1069b's atmosphere is the key to its habitability, can we ever actually see it? Right now, the brutally honest answer is not in the clean, elegant way we've used for TRAPPIST-1. For many of the most famous Earth-like exoplanets, we rely on transits. The planet passes directly in front of its star. A thin ring of starlight filters through the atmosphere, and we split that light into a spectrum. That technique, transmission spectroscopy, lets us read the chemical fingerprints of gases like water vapor or CO2. But while TRAPPIST-1's planets obligingly cross their star, Wolf 1069b does not. As far as we can tell, its orbit is tilted just enough that it never silhouettes itself against the stellar disk.
This means our most powerful atmospheric tool is simply turned off. So let's begin with what that forces us to do instead. Without transits, we have to chase the planet's own light. We can try to separate the faint glow of Wolf 1069b from the much brighter red dwarf using high-resolution spectroscopy, looking for tiny spectral lines that shift back and forth as the planet orbits. In principle, reflected starlight on the day side, or thermal emission from a warm surface or atmosphere, will wobble in velocity relative to the star. If we stack enough data, those lines could betray the presence of molecules. It should be noted that this is extremely hard. Wolf 1069b is small, dark, and only about 31 light-years away, which is close in a galactic sense, but still unimaginably distant. Phase curve measurements, tracking how the total brightness of the system changes as different portions of the planet rotate into view, could hint at whether heat is being redistributed by an atmosphere, or whether we are looking at a bare rock with a blazing day side and a frozen night side. In the hunt for alien life, even a crude temperature map is gold. Direct imaging is the dream. One day, high-contrast instruments might literally pick out the planet as a separate point of light next to its star and feed that light into a spectrograph. For a dim red dwarf like Wolf 1069, the contrast is slightly more forgiving than for a sun-like star, but we are still talking about technology that pushes far beyond JWST. Optimistically speaking, the next generation of ground-based giants, the extremely large telescope in Chile, the 30-meter telescope, and the giant Magellan telescope could be the game changers. Their enormous mirrors collect far more photons, and their advanced spectrographs can slice the spectrum into incredibly fine detail. Over many nights, they might tease out broad signatures. Is there an atmosphere at all? Or is the thermal pattern consistent with airless rock? Do we see hints of a greenhouse blanket dominated by CO2? Or something more Earth-like that smooths out the temperature extremes of a tidally locked world in the Goldilocks zone? So it's time to find out the truth. Wolf 1069b is just beyond our current reach, but not forever. The first real constraints on its air may arrive within a few decades, and when they do, we may face an even deeper question. If this world turns out to be truly habitable, what could actually live there? What would alien life there look like to us? If life really exists on Wolf 1069b, what would it actually look like to us from 31 light-years away, through nothing but starlight and noise? We will not see oceans or forests directly. In the hunt for alien life, what we really see first are patterns in light. So let's begin with the classic atmospheric biosignatures we would hope for. On Earth, one of the strongest clues to life is the strange partnership between oxygen and methane in our atmosphere. Oxygen is so reactive that left alone, it would quickly rust the planet and vanish into rocks and oceans. Methane is easily destroyed by sunlight, yet both gases persist together because biology keeps pumping them out. This means that for Wolf 1069b, a steady mix of oxygen with something like methane, nitrous oxide, or even certain sulfur compounds would be a powerful hint that something on the surface is metabolizing. But while those combinations are our standard playbook, Wolf 1069b orbits a cool red dwarf, and that changes the rules. The star's spectrum is redder, with fewer energetic ultraviolet photons. Photochemistry in such an atmosphere would run differently, breaking and building molecules at new rates. Oxygen might build up more slowly, or not at all, even if life is present. It should be noted that on a tidally locked planet with a permanent day side and night side, circulation patterns could trap gases or create long-lived chemical pockets. In that case, we might see an atmosphere dominated by carbon dioxide, hydrogen, or even exotic organic hazes, while biology hides in the details of trace gases. Then there is the surface itself. On Earth, plants imprint a sharp red edge in our reflectance spectrum, where leaves suddenly become much more reflective in the near infrared.
Around a red dwarf, however, photosynthetic pigments might shift their absorption deeper into the infrared to match the star's output. So instead of a red edge, Wolf 1069b could host a near-infrared edge, or several edges from different alien pigments. Imagine a hemisphere where the substellar region glows slightly brighter in specific infrared colors, not because of lava or ice, but because of forests of organisms adapted to perpetual twilight.
Pattern interrupt. What if there is life but no oxygen at all? An anoxic biosphere, more like early Earth, could still leave subtle fingerprints, seasonal swings in methane, or complex organic hazes that change with the planet's orbit. How would we ever see such delicate signals on a non-transiting world? Future giant telescopes, both on the ground and in space, could use high-contrast imaging and coronagraphs to separate Wolf 1069b's faint glow from its dim star. With enough collecting area and time, we could spread that light into a spectrum and search for these chemical and surface signatures, line by line. Optimistically speaking, a century from now, we might detect a strong oxygen signal from this planet. Would that be enough to declare life? Probably not. We would still wrestle with exotic abiotic explanations, oceans boiled away by an early flare phase, leaving oxygen behind, or unusual water loss pathways under a red dwarf spectrum. So it's time to find out the truth by combining multiple lines of evidence, gases, surfaces, and variability before we dare to say that Wolf 1069b is alive. Could we ever go there? So if Wolf 1069b did show hints of life in its atmosphere, could we ever go there ourselves? In the hunt for alien life, that is the next, almost uncomfortable question, because it forces us to compare our dreams with the hard reality of interstellar distance. Wolf 1069b is about 31 light years away. What does that actually mean? With current chemical rockets, a fast probe might reach a few tens of kilometers per second. This means it would need on the order of hundreds of thousands of years to cross that gap, far longer than human civilization has even existed. Even if we used more speculative propulsion, like nuclear fusion drives or powerful light sails pushed by lasers, we are still talking about journeys lasting decades to centuries. So let's begin by accepting that any mission would be a project for many generations, not a single lifetime. It should be noted that such timescales create brutal engineering and biological challenges. How do you keep a spacecraft functioning for 100 years? Electronics age, materials crack, tiny impacts accumulate. Life support for humans would have to recycle air, water, and nutrients almost perfectly, while shielding them from cosmic rays and particles from the interstellar medium. And what about communication? Even at light speed, signals would take 31 years to go one way. You ask a question, your grandchildren hear the reply. Because of this, the first visitors to Wolf 1069b would almost certainly be robotic. We can imagine a flotilla of hardened probes breaking into the system, adjusting their orbit around the red dwarf, and then dispatching landers or atmospheric skimmers. They would map the planet's surface in exquisite detail, trace the sharp divide between the sunlit hemisphere and the frozen night, and zoom in on the permanent twilight ring where a habitable climate might exist. Can you picture the first real images of an Earth-like world with no sunrise, only a star frozen above the horizon? If those images revealed oceans or clouds, the next question would be whether humans could live there. Optimistically speaking, in a truly habitable scenario, our colonies would probably hug the Terminator band, where temperatures stay moderate. Cities might be built in long arcs, always facing the same point in the sky, with solar arrays permanently locked onto the star's position. On the day side, we might harvest relentless stellar energy. On the night side, we could mine volatiles and use the endless dark for observatories peering deep into the universe. But how would we adapt psychologically to a world without a rising or setting sun?
Would we impose artificial day-night cycles with lighting and architecture, or embrace the strange constancy of the sky? So it's time to find out the truth about what long-term human health, culture, and even language would look like on such a planet.
All of this lies far beyond our current capabilities. Yet thinking concretely about life on Wolf 1069b is not just science fiction decoration. This means we can work backwards. What propulsion, radiation shielding, autonomous repair, and closed-loop habitats would we need to make such a journey plausible? In the next section, we will turn from distant voyages to something more immediate: how upcoming telescopes can probe this world without leaving home at all. The most likely Wolf 1069b we'll never see. So if we try to put all of this together, what is Wolf 1069b actually like right now? In the hunt for alien life, this is where we have to stop daydreaming and place a careful bet. We have 3 broad atmospheric stories on the table. In one, Wolf 1069b is wrapped in a thick CO2 greenhouse, more like a dimmer, slower Venus than an Earth twin, with heat efficiently smeared from its perpetual day side into the night. In another, it carries an Earth-like atmosphere of nitrogen, oxygen, and a bit of CO2, producing milder temperatures and perhaps clouds over a liquid ocean at the substellar point. And in the third, the planet lost almost everything long ago, leaving only a thin wisp of gas, or almost no atmosphere at all, its day side baked and its night side frozen. But while all 3 are physically possible, not all are equally likely. Red dwarf stars spend their youth flaring violently, stripping atmospheres. Yet Wolf 1069 today is unusually quiet for a red dwarf. This means the planet may have been battered early on, then left in relative peace for billions of years. A runaway Venus-style atmosphere would require huge initial volatile inventories and sustained heating. A totally airless rock would require that early activity to erase every trace of gas and water. So let's begin to narrow it down. The most plausible middle ground is that Wolf 1069b kept a substantial atmosphere, probably thicker and richer in CO2 than Earth's, but not crushingly dense. Climate models for similar worlds show that even a few bars of CO2 can keep surface liquid water stable on parts of a tidally locked planet, especially near the day-night boundary. Optimistically speaking, that gives us at least scattered seas or lakes in a temperate ring. It should be noted that there are still huge unknowns. How much water did the planet start with? Did a magnetic field shield its air from the worst of the young star's wind? Or was it peeled away layer by layer? Did early flares sterilize the surface, or simply reshape the climate before calming down? A slightly wetter birth, or a slightly stronger field, could be the difference between a cool oceanic terminator and a dry, dusty desert world. If we could stand there, what would this most likely Wolf 1069b feel like? Under a permanent red sky, the star would hang motionless, a dull ember on the dayside horizon if you live in the habitable twilight ring. Winds would race from hot day to cold night, howling through valleys as the atmosphere endlessly tries to balance the temperature contrast. Ice might creep in from the night side, while darker rock and water absorb heat closer to the light. So it's time to find out the truth. Can our telescopes actually test this picture? Or will Wolf 1069b remain a beautiful guess? In the next section, we will see how future observations might push this world toward Eden, Iceball, or something far stranger than either. What Wolf 1069b teaches us about our own future. So if we can turn a dim, pixel-sized world into a climate story, what does that really change for us? And what does a planet like Wolf 1069b say about our own future in the universe? Evaluating habitability used to mean asking a simple question. Does it look like Earth?
blue oceans, white clouds, a 24-hour spin, a comfortable distance from a sun-like star. But while that picture is emotionally powerful, it is scientifically narrow. Wolf 1069b forces us to expand that definition of Earth-like to something deeper, not the scenery, but the physics. This means gravity, temperature, and long-term energy balance, even if the sky is red and the day never ends. On Wolf 1069b, no sunset is not a poetic phrase. It is the geometry of the orbit. One hemisphere bakes in unending daylight, the other freezes in eternal night. Habitability, if it exists, might live in a ring of twilight, a permanent Goldilocks zone along the Terminator. In the hunt for alien life, that is a radical shift. We stop searching only for twins of our world and start searching for cousins that share the same underlying rules, expressed in very different ways. It should be noted that this change in perspective also throws Earth into sharper focus. Our climate balance depends on a delicate dance between rotation, atmosphere, and a relatively stable yellow star. Wolf 1069b shows us that even with similar mass and insolation, a different rotation state or host star can create a completely different surface reality. If a slightly stronger greenhouse there is the difference between an ice-locked rock and a habitable ocean, what does that say about our own vulnerability to pushing Earth's atmosphere out of its narrow range? Here is the pattern interrupt. We usually imagine alien life under blue skies. But what if the most common biospheres are lit by dim, red suns in eternal evening? Red dwarfs dominate our galaxy. Optimistically speaking, if life can adapt to the slow, steady output of a quiet red dwarf like Wolf 1069, then the universe might be full of ecosystems that never see a true sunrise or sunset, forests frozen in twilight, oceans glowing under a fixed star, civilizations that never invent time zones because the sky never changes. So let's begin to think forward. Over the next century, worlds like Wolf 1069b will guide astronomy, astrobiology, and even our science fiction. Climate models will test how atmospheres circulate on tidally locked planets. Telescopes will chase faint hints of oxygen or methane in strange, skewed spectra. Writers will imagine cities clustered around the substellar point, or nomadic cultures migrating around the Terminator line. And us? Wolf 1069b becomes a mirror. It reflects not only new places where life might exist, but new ways our own descendants might live, on planets where the star hangs motionless, where Earth-like means familiar chemistry and stable energy, not familiar skies. So it's time to find out the truth. Are we a rare exception, or just one expression of a much broader cosmic pattern? In the next section, we will see how our instruments and our imagination might finally bridge that gap. From eternal sunset back to your night sky. So where does that leave us after this journey to a world where the sun never moves? We began with a simple, unsettling question. What would life be like on a planet locked in an eternal sunset? From there, we traced our way outward from our own spinning Earth to a small red dwarf in Cygnus, just 31 light-years away. Wolf 1069 is not a dramatic beacon in the sky. It is a quiet, cool star. Yet around it, the radio velocity data revealed something extraordinary. A rocky planet, roughly Earth mass, sitting in the Goldilocks zone. In the hunt for alien life, that combination is like a bright flag planted in the darkness. But while the phrase Earth-like is tempting, we quickly saw how misleading it can be. This planet almost certainly keeps the same face to its star. One hemisphere is locked in permanent day,
the other in endless night. So instead of a rising and setting sun, we imagined a sky where the red dwarf hangs motionless, a dim ember frozen above an alien landscape. It should be noted that this single fact, tidal locking, reshapes everything about climate, weather, and habitability. This means the key question becomes, what kind of atmosphere, if any, does Wolf 1069b actually have? We step through the possibilities. With no atmosphere, the day side bakes and the night side freezes, a sterile rock split between furnace and ice. With a thin one, perhaps there is some heat flow, but still no stable liquid water. With a thick, CO2-rich blanket, global winds could carry warmth into the darkness, keeping the twilight ring mild and, just maybe, wet. In that scenario, the picture turns vivid. Imagine walking in the habitable band where day meets night under a deep red sky. To one side, the star glows low and permanent. To the other, stars are already visible in an eternal pre-dawn. Oceans or lakes might cluster here, ringed by ice deserts on the night side and bright, cloud-laced glare toward the substellar point. Could photosynthetic life adapt to that fixed crimson sun? Could other forms thrive in the dimmer, scattered light along the terminator?
Optimistically speaking, Wolf 1069b is one of the most promising nearby rocky worlds we know. Close, temperate in the right conditions, orbiting a relatively calm red dwarf that may have spared its atmosphere the worst flares. Yet our certainty stops at the edge of our instruments. The planet does not transit, so we cannot easily read its atmospheric fingerprint the way we do for TRAPPIST-1. For now, we rely on models, simulations, and careful inference. So let's begin to bring this back to your own night sky. The next time you step outside and look towards Cygnus, you can carry this mental image with you. A real planet, invisible to your eyes, may be living out one of the stories we have drawn. Airless rock, steam-shrouded hothouse, or a thin ring of habitability clinging to eternal twilight. Which is it? In our final section, we will see how the next generation of telescopes might finally turn that distant, frozen sunset into hard evidence. Your turn to choose. Wolf 1069b's fate. So it's time to find out the truth. We have drawn 3 very different futures for this distant world, all from the same sparse data, all orbiting the same quiet red dwarf. But which Wolf 1069b feels the most real to you? Is it the thick greenhouse ocean world with a deep global sea hiding beneath a heavy CO2 atmosphere, its substellar point a permanent glinting eye of reflected light? In that version, a day in the life might mean drifting under a dim reddish sky, with the star frozen overhead and slow, planet-wide winds endlessly trying to move heat from light into darkness. Do you imagine floating plankton analogs or towering hydrothermal vents on a tidally stressed seafloor, feeding alien ecosystems in the dark? Or do you prefer the Earth-like twilight paradise, a narrow Goldilocks zone painted as a ring around the terminator? Here, an explorer could walk from blazing, cloud-thick day into airless night in a single journey, watching the star sink sideways instead of setting. In the hunt for alien life, this thin, habitable band may be the most poetic, a place where forests of ice crystals give way to liquid lakes, and every direction leads either to fire or to frozen vacuum. Perhaps, though, you are most compelled by the stark, airless rock with hidden subsurface life. No atmosphere, no oceans, just a frozen, cratered surface, while deep below, salty pockets of water cling to warmth from the planet's interior. In that scenario, a day is meaningless, but microbes near chemical energy sources might not care. This means that even a world that looks dead from orbit could still be quietly alive.
Which of these three stories do you find most convincing, and why? Tell us your own day in the life on Wolf 1069b in the comments. Use the physics we have explored, tidal locking, heat transport, fragile atmospheres, as your playground, and then let your imagination build cities, oceans, or cavern networks on top. It should be noted that this is not the end of Wolf 1069b's story. As new telescopes come online, from JWST follow-ups to the giant observatories now rising on Earth, we will return to this planet and others like it. Optimistically speaking, each new spectrum, each new constraint on an atmosphere, brings us closer to saying something definitive about worlds we can never visit. So let's begin a wider journey. If you want to compare Wolf 1069b to other red dwarf systems, take a look at our deep dive on TRAPPIST-1 next, and see how 7 tightly packed planets rewrite the rules of what a habitable system can be. Subscribe if you want to follow future updates, not just on this planet, but on the growing family of nearby Earth-like worlds. In the end, every planet we study is a test of a single question. How many ways can the universe find to make a home for life? And somewhere, just beyond our current reach, the answer is already written in an alien sky we have not yet learned to read.